So next speaker in this session will be Hari K. Hari, can you please share your screen?
Yes, just a second. Is my screen visible?
Yes, we can see.
Oh.
So next speaker is Hari K from IIT Madras, and he'll be talking about tidal versus absolute acceleration effects on Rindler groups. Hari, you have 12 minutes. I'll give you a reminder at 10.
Okay, sir. Thank you. So, good afternoon, everyone. I thank the organizers for inviting me. So, I am Hari K. I'm from the Department of Physics, IIT Madras. The title of the talk is Tidal versus Absolute Acceleration Effects on Rindler probes. So, this is the work I have done with my supervisor Daud Kutwala, and you can see the references here if there are any doubts, further doubts. So let me give a outline of the talk. So I will be starting with a brief introduction and try to motivate you. Then I will just set up the problem. We will give a geometrical idea about the setup of the problem. Then I will move on to the special case, and I will also, in the setting up of the problem, I will also give some results and give the main results, and that results will be applied to some of the symmetric spaces. Then we will see the some of the applications where our results can be applied. Then I will summarize the talk. Okay, let me start with a brief introduction. So the accelerated frames in flat spacetime together with equivalence principle is used to understand the processes in curved spacetime. So one textbook example is about Hawking radiation and can give or get good insights from the flat spacetime effect such as Unruh effect. So such things are done to understand the processes in curved spacetime. But there is a problem. The problem is that whenever we combine flat spacetime with equivalence principle, we tend to ignore the tidal acceleration due to the background curvature. So in this work, we will be concentrating on how we can include those tidal effects into the accelerated probe. And how we are doing? So we are trying to capture these effects using the relation between the geodesic distance and proper time of the trajectory. Okay, so this relation is also very useful in studying Unruh detectors, and classically it's interesting to study the differential aging of twins, and it also gives good insights into the thermal properties associated with the accelerated trajectory. So this is a good enough motivation to study this. And also the problem is that with available expansion in the literature, it is not clear how the curvature gives good contribution in this relationship. The best we get is to fourth order, which does not have any curvature contribution, and the next order, in the sixth order, we have some curvature contribution, but it will not give any insights as our results. Okay, so let me give an analog idea or geometrically give you an idea about what we are doing exactly. So just consider a circular sector. Point A and B is connected using arc of the circle and through a straight line. So the arc of the circle, I am denoting it as the tau acceleration, delta tau acceleration, and the straight line connecting point A and point B is the tau geodesic. And you can easily find that this is related using this expression. And similarly, if you go into Minkowski spacetime, then you can see the constant accelerated Rindler observers have a same feature like this, and we can also obtain the same equation, which is you can compare it with the ordinary Euclidean equation, and you can see the sine is replaced by sine hyperbolic and constant radius is replaced by constant acceleration. So this is the geometrical setup. This is the motivation, and we will try to set up this problem in a curved spacetime. Okay, so if you look at the right hand side figure, this is the geometrical setup of our problem. So you have an accelerated curve. I hope you can see my cursor. Can you confirm?
Yes, we can.
Okay, thank you. So this is the accelerated trajectory we given by script C, and we are considering 2 points on the trajectory, P0 and P, and we are also considering a geodesic connecting P and P0. So there are two curves, C, which is the accelerated trajectory, and G, which is the geodesic trajectory, and UA is the forward acceleration on the accelerated trajectory, and TA is the tangent vector to the geodesic. So we are constructing Riemann normal coordinates at this P naught, which is our base point. And these are standard definitions from Riemann normal coordinates. And we will be constructing a coordinate ZA, which is equal to our Riemann normal coordinates to obtain this equation. This just come from the definitions of Riemann normal coordinates. So here we relate tau geodesic to tau acceleration. So to find Z set, we are expanding it in Taylor series. We are using the Taylor series expansion. And here notice that these are just ordinary derivatives. We need to convert it into covariant derivatives to make our expression covariant. So to simplify the Taylor series expansions, we are using two assumptions. One is that the motion will be hyperbolic with the help of what we call as Rindler conditions. They are the actual definitions is that the acceleration, the magnitude of the acceleration will be constant. So it will help us to reduce the derivatives, to write the derivatives in terms of, again, for velocity and for acceleration. And the second assumption is that the derivatives of the curvature tensor itself are small. And with these two assumptions, we can relate the first derivative of Z with Uy and the second derivative of Z with acceleration. And the successive derivatives are obtained from differentiation of the definition of acceleration. So these are the technical part. So I'm skipping the intermediate steps because they are lengthy, and we have also used like many manipulations, and we have also implemented what we call a software called Cadabra, which is a symbolic package. And using those implementation, we have obtained an equation for a relation between the tau geodesic and tau acceleration, the geodesic distance and the proper time of the accelerated trajectory. And notice that here script E underscore N is the tidal part of the tensor, Riemann tensor. And here you can see our ABCD is dotted with UA and NB. So here U is the tangent vector for velocity, N is the N is the unit vector in the direction of acceleration, which is normal to the direction of tangent. And here RA represent collectively the terms which at least one index will be dotted with not zero or neither zero or nor none. So there will be some other indices in other than in U and N plane, U and plane. So the main observation or the key result of our work is that we could actually sum this expansion, this series, into a nice analytic form given by this expression. And here RA, you can see it is the odd one out here because the other terms are nicely summed into this form, but RA, we couldn't find a nice summation. Now let us apply these results to some more interesting spacetimes. So let us move on to some symmetric spaces. So first we will discuss on maximally symmetric spacetimes. So for a maximally symmetric spacetime, RA will be 0 due to the structure of Riemann tensor, and the gradients, the nabla RABCD will be also 0. So we will be getting an exact relationship between tau geodesic and tau acceleration. And for static spherically symmetric spacetimes, if you are considering the observer moving in TR plane, we are using the coordinates TR theta phi, and if the observer is moving in TR plane, again we can prove that RA will be equal to 0. And there one problem is that the derivatives or gradients in RABCD will not be equal to 0, but then our results will only be approximate, and that will be a best approximation we can obtain. And let us see how we can apply these results. Some of the application, the first one classically is the twin paradox because the geometrical setup is very same. And here you have two twins actually starting from P we can discuss. So two twins are separated. One twin is accelerated. It has a constant acceleration, and the other twin is following a geodesic curve. And finally, they are meeting after some time and at P naught. Then you can relate the differential aging of two twins using our expression. So in literature, we have already seen they have done for de Sitter and anti-de Sitter, and our results agree well with those results. And for other case, we can discuss about the radial motion of the same twins in Schwarzschild. And here there are some small variations due to the existence of gradients in RABCD. So we'll just this is a plot which compares different the relationship in different spacetimes, and here you can see in anti-de Sitter there is a bound on the relationship. And moving on to the quantum mechanical properties, if I set up a two-level quantum detector, onto DV detector, we can see how the response function will behave. So here it depends on the Whiteman 2.0. I'm skipping the details. We are only focusing on the sigma square, which is the geodesic distance. So other terms will not have much contribution, and already they have studied. So we will be focusing on what will the contribution do to the sigma square. So if you try to do the Fourier transform, we will obtain the equation of this form. And here you can notice the important point is that the effective temperature is given by this expression, which is a combination of a square minus this tidal term. And if we apply the same for spherical symmetric spaces, you can see this will be the tidal term from the metric. And if I again use it for maximally symmetric spacetimes, you will obtain a very nice Pythagorean sum. And this is actually this was actually initially given by Desser and Levin by something called GEMS approach. So we could actually derive this result in the same way, and we could generalize the expression to other spacetimes for a general case. And let me go to my last application, which will be equivalence principle. So using our result, we can state some observations which we made with the equivalence principle. Let me start with a static detector in the static spacetime. So the killing vector will be given by this equation, and the detector will respond to the acceleration corresponding to A effective, which is given by 1 by n root of k kappa square minus n square En. And here kappa by n is the magnitude of acceleration of the detector, and kappa at the horizon, it will be surface gravity. And if you look at n tending to 0 limit, the equivalence principle holds because it will be very near to the horizon, and the acceleration term will be dominating over the tidal term. And if I look for other observers which are not near to the horizon, then we can see that in the local frame of the observer can measure an acceleration of kappa by n. So he or she can put a rocket in his frame and measure its local acceleration, which will be equal to kappa by n. But if we look at the detector response of the same observer, the detector will respond to an effective acceleration of this A effective, which was given in the last slide. And we can see if we are using two different methods, we are getting two different accelerations. So since A is not equal to A effective, the observer can actually distinguish between the acceleration effects and the gravitational effects in his or her local frame. So we found that this is at variance with the equivalence principle. So let me summarize my talk, and this is the conclusion and summary. And you should note that our method was actually useful because the ordinary Taylor expansion will not give such insight between the interplay between tidal and tidal versus absolute acceleration. So that's all. Thank you all.
Thank you, Hari. And also thanks for keeping in time. Shriram, you have a question? Please go ahead.
Yeah, Hari, you mentioned in one of your slides that you're taking only one part of the Green's function to calculate the detector response and interpret.
Yes.
Yeah, the next one, right? Now, my concern is that you are focusing on trajectories where there is time translational invariance. There is a killing vector, correct?
Yes.
Okay, in which case, why are you limiting? Why is there an upper limit to this integral? Typically, it is integrated over all time, right?
Yes, but if you are using a switching function, we can actually restrict it to.
I agree, but the switching function will also introduce its changes as well. My concern is that if you are integrating over all time, can you just chop off a part of the Green's function and consider it? That is my question.
Okay.
Is that consistent is my question. That's all.
Okay. I might have to think about that.
Sure.
Okay.
Yeah. Whether, some of the conclusions will be affected by it was my concern.
Okay.
Thank you.
Okay.
Yeah.
Amitav, you have a question? Please go ahead.
Yeah. So Hari, you presented this resummed formula that
yes.
in terms of the square root. Actually, my question is, so the the derivation is based, so the first main equation is based on this Riemann normal coordinates which are set up at point P0.
Yes.
And the assumption is that both the geodesic trajectory and the accelerated trajectory are within this Riemann normal coordinates.
Yes.
Then how do you know that this resummed formula is valid? I mean, because I mean the resummed formula seems to be like going far away from the, I mean, can it be, you are applying it to situations which are not necessarily in this Riemann normal coordinate system. I'm slightly confused about this.
But our equations are actually covariant in this region. So we can, because we are converting all the ordinary derivative into covariant derivatives. So
the coordinates are only valid very close to that point. They are not valid beyond that point. Coordinates are only valid near P0. They are not valid far away from P0.
But once they are resummed, we can actually, like, it's just like the Taylor expansion, validity of the Taylor expansion, right? If the radius of convergence, it depends on the radius of convergence. So it's the same problem here also, right?
Yeah, it's the same issue. Yeah.
So, but we are also assuming that the gradient of the RABCD will be small, very small. So in that cases, I think the if we write the expansion in terms of covariant derivatives and resum it, it won't be a problem. But it will be a problem, I think, when the derivatives of curvature is large enough and it has some contribution in that.
Okay. And just one comment. So you mentioned this Desser and Levin paper.
Yes.
So actually, Desser and Levin also show that spherically symmetric spacetimes can be embedded in sufficiently higher dimensional Minkowski spacetime.
Yes. Yes.
So that result can be used to correct, perhaps correct your because you were having some approximation issues with the spherically symmetric spacetime. Yeah.
Yes. Okay. Yeah. That is a valid point. Yeah. We will try to see something can be done.
Okay. Any other questions? I don't see any raised hands. So in that case, let's thank Hari once again.